Welcome to the course on error control coding and introduction to convolutional code. We are going to continue our discussion on decoding of convolutional codes. In the last class, we talked about Viterbi decoding, and if you recall, Viterbi decoding is an efficient algorithm to compute a path to the trellis of a convolutional code. Now, it essentially finds out, Viterbi algorithm essentially finds out an estimate of the code word, because any path through the trellis of a convolutional code is basically a code word. Now, that not necessarily minimizes the bit error rate probability. In many applications, we are interested to minimize the bit error rate. So, today we are going to talk about a decoding algorithm which is basically going to minimize bit error rate probability, symbol error rate probability. So, we are going to use a posteriori probability based algorithm to estimate our information sequence, and this algorithm which maximizes probability of u hat given u given the received sequence R is known as map decoder. Now, this is also known as BCJR algorithm, named after these researchers who Bail, Koch, Jelinek and Raviv, who introduced this algorithm in 1974. And this algorithm can be applied to any linear code, block code or convolutional code. Now, the complexity of this algorithm was much higher than Viterbi algorithm, and that is why it was not popular in 70s, but in late 90s when this concatenated codes, turbo codes came into picture and we required soft estimates, then these algorithms became very popular. So, what this algorithm does, it computes the a posteriori probability. So, I define a posteriori log likelihood value, I call it L value like this. So, it basically computes probability of UL being +1 given a received sequence R by probability of UL being -1 given received sequence R. Take a log of that. Now, if this L value is greater than 0, then you decide in favor of UL being +1, otherwise you decide in favor of UL being -1. So, your decoder output will be +1 if the L value is greater than 0, otherwise you decide in favor of -1. So, we are going to now talk about how to compute these terms. These terms you see in computation of APP value, how do we compute these terms and how we can exploit the structure of the trellis of the convolutional encoder to simplify this expression. So, let us look at this probability of UL being +1 given a received sequence R. This can be written as joint probability of UL being +1 and received sequence R divided by probability of receiving this R. Now, this probability of UL being +1 given a received sequence R can be written as probability of R given V multiplied probability of U sum over all input sequences that belongs to the set where UL is +1, and this can be written as probability of R given V multiplied by probability of U sum over all input sequences. So, as I said, since we are interested in joint probability of UL being +1 and R, we sum this probability over all those set of information sequences where the bit, the corresponding bit is +1. and our transmitted code word is V, our information sequence is U, and R is the receive sequence. So, probability of R given V can be computed from the channel, given channel. Similarly, we can also compute. Now, if you go back here, the denominator we need to compute probability of UL being -1 given R. So, similar to this term, we can also write probability of UL being -1 given R, and probability of R is a common term. So, if we do that, what we get is this. So, again this L value, the APP value of U of L is given by probability of R given V multiplied probability of U, where we are summing over all information sequences where the corresponding bit is +1. And similarly, for the denominator we are summing over all information sequences where information bit is -1. We will illustrate this with an help of example, and then things will be little more clear. Now, note here, if you have very large sequences, this is sum over all input sequences where UL is +1, and this sum over all input sequences where UL is -1. So, if your information sequence is large, this is sum over very large number of possibilities. So, this is quite complex. Now, can we use the structure of the convolutional code to simplify this expression? The answer to this is yes. So, we are going to basically simplify this equation 4 by using the trellis structure of the convolutional code. We know all possible transitions are not possible. So, our trellis diagram or the state diagram will tell us what are the valid transitions. So, we can simplify this expression using our valid state transitions. So, what we are going to do is we are going to make use of the trellis structure of the code to simplify our equation number 4. So, let us see how do we do it. So, again we go back and look at this probability of UL being +1 given our receive sequence R. As we have written, this can be written as joint probability of UL being 1 and the probability of receiving R divided by probability of R. Now, we are going to now look at this expression. This is joint probability of UL being +1 and given the receive sequence R has been received. So, if you look at any trellis diagram, let us say this is some trellis diagram, just simple 2-state code, and like that you have so, we are interested in where UL is +1 and where U is -1. Let us say this is 0 by 0 0, this is 1 by 1 1, this is let us say 1 by 1 0, this is 0 by 0 1. So, let us look at one trellis section. So, we are interested in all those transitions which belongs to UL +1. Now, what are those transitions? So, in this example, this is one such transition and the other is this transition. Okay. So, what I am writing here is then I am interested in what is the joint probability that the previous state is S hat S prime, the next state is S and the receive sequence is R, and I am summing over all those state transitions that belong to the set pair where the input corresponds to this transition is +1. So, note what is my this sigma L plus It is the set of all state pairs where the initial state is S prime, the next state is X. So, it is a pair of states where the transitions, the input bit corresponding to a valid transition is +1. So, in this case, the set that belongs to this is given by this red line. Okay. So, I can write the joint probability of UL being +1 and R in terms of condition on the valid trellis transitions in this way. I can write it as what is the probability that the initial state is S hat, next state is S, given that I have received sequence R, and I sum over all those transitions which belong to input bit being +1. Similarly, I can write exactly the way I wrote probability of UL being +1 given R. I can follow the same procedure to write what is the probability of UL being -1 given R. So, what will be the change here? So, I will compute this probability and I will sum over all those state pairs which corresponds to input bit -1. So, if I plug these values of probabilities which are given by equation 5, and similarly I can calculate the probability of UL being -1 given R. So, instead of this thing here, I will have summation over S at S, summation over all those pairs which corresponds to UL being -1, and I will get this same thing here. So, if I do that, what I will get is equation number 6. So, note that previously I had the same expression, equation number 4, in terms of this input sequence UL. Now, if our input sequence is very long, this is summation over a large number of terms, whereas I have now simplified my expression. So, this summation is now only over valid transitions corresponding to UL being +1, and this summation is over valid transitions corresponding to UL being -1. So, I have simplified my equation number 4 in equation number 6, and I have used the state diagram or the trellis diagram of the convolutional encoder to simplify my expression. So, this will be my a posteriori probability log like L value a posteriori probability. Now, how do I compute this term? This we will show that if we can write this term as product of 3 terms, and 2 of these terms can be computed recursively. That is what I am going to show in the subsequent slide. So, let us look at this expression. How do we compute the probability that in the current state it is in S hat, next state is S, given a received sequence R. So, as I said, we are interested in this. Now, this can be written as, so I have this received sequence R. So, let us say this is R at time t equal to 1, t equal to 2. So, this is my, let us say, time instances, and I get some bits. Let us say I get some R1 corresponds to what I receive at time t equal to 1, R2 corresponds to what I receive at time 2, RL corresponds to what I receive in time L, and like that. RL plus 1 is what I receive at time t equal to L plus 1, like that. So, this receives, this whole thing is my received sequence R. Okay. Now, what I am doing is I am partition that received sequence into 3 segments. So, one which corresponds to, one is this which corresponds to time before L. So, one is this portion of my received sequence. This is R t less than L. Next is this section, which corresponds to R T greater than L, and then third section is this, which corresponds to R L. Okay. So, what I did was I split this R into 3 segments. One is R corresponds to time less than L, R at time L, and R at time greater than L. Now, using Bayes rule, I can write this probability as probability of R at time greater than L given S prime and S, and these are into probability of S prime S and R at t less than L and R L. Now, subsequently, I can further simplify this, again apply Bayes rule, and I can write this as probability of S and R L given S prime and R T less than L into probability of S prime and R T less than L. So, note now this term that I had here. So, applying Bayes rule, essentially I broke it up into 3 terms. One is this term, second is this term, and third is this term. Okay. Now, let us look at this. So, probability of R when t is greater than L given initial state S prime, next state S, and the receive sequence before L and receive sequences L. So, let us look at the trellis diagram. Let us go back and look at the trellis diagram at time L. Let us take this example of 2 state code. So, what I had here was 0 by 0 0, 1 by 1 1, then I had this 1 as 1 0, and this was 0 by 0 1. So, this was my trellis diagram. This is all 0 state, this is state 1. Okay. Now, note, and like that you have in trellis diagram, you have this is one trellis section, you will similarly have trellis sections other. So, this is a time L. So, you are interested in what is the probability of R t greater than L given previous state S hat, given next state S, given the receive sequence before time t equal to L, and given the current receive sequence. Now, note that if I specify this next state, so probability of R t greater than L given S, then I do not need information about the previous state, I do not need information about what is the current input, I do not need information about what was the receive sequence before L, provided I know what is the next state S. So, this probability that you see here, probability of R t greater than L given S prime S and this receive sequence R, can be then written as probability of R t greater than L given only S, because knowing this final state S, I do not need information about what was my state here, I do not need information about what my receive sequence was here, I do not need information about what my past receive sequence was, provided I know what was my next state S. So, this given these quantity will only depend on S. So, I can simplify this expression like this. Now, same thing here, look at probability of being S R L given previous state and given the input before time t equal to L. Now, if I specify what the previous state is, then I do not need what was my input at time t less than L. So, this can be simplified into this expression, and then of course, we have this third expression, which is this. So, what we have done is this joint probability we have now split up into 3 probabilities, one is this, second one is this, and third one is this. Okay. And we will now show how we can compute each of these terms. So, let us call this probability by alpha, this probability by gamma, and this probability by beta. And now we are going to show, then we can write then this joint probability in terms of alpha, beta and gamma. So, we can now write our equation in terms of alpha, beta and gamma. Okay. So, let us now talk about how we can compute alpha, beta and gamma. So, this alphas can be computed using forward recursion as follows. So, let us look at what is alpha plus 1 s. Now, go back to our definition. It is a probability, joint probability of being in state s prime and receive sequence at time t less than l. So, alpha l plus 1 from definition can be written like this. Now, I can write this as, so I am adding a new variable which is the next state s, and I am adding a new variable which is next state previous state s hat and summing over all previous state. So, what is this? Summation over s hat belonging to all possible state at time l. So, what I did was, so I had some term, probability of let us say a b, and what I did was I just added a term probability a b c and I summed over all possible values of c. So, that is what I did here. I introduced a new variable s prime and I summed over all these probabilities, all these possible values of s prime. Now, this term can be written as product of these two terms. This is following exactly the same procedure which we followed here. When we wrote this, we are basically using base rule. Now, using base rule, basically I can write this probability as product of these two probabilities. Now, again the probability of S and RL given S prime and received sequence at time t less than L. If you know the previous state S prime, you do not need this information. So, then this probability can be simplified to this probability and this is this. Now, what is this term? This term is basically by definition our alpha, and what is the next term? This is our gamma. So, what I have shown you here then is alpha at next state S can be written as, can be computed recursively from alphas at previous state in this particular fashion. So, again let us illustrate this with an example. Let us go back to our 2 state code example. So, this is 2 state code, this is my all 0 state, this is state 1. So, there are 2 transitions, let us say this is 0, input output 0 0, input 1 output 1 1, here input 1 output 1 0, and here input 0 and output 0 1. So, then what would be the value of alpha? So, let us say this is time t equal to some L and this is time t equal to L plus 1. So, how can we write let us say alpha at L plus 1 for the state 0? Now, note here this is given by product of this summation over all input state, right. Now, so alpha L 0 can be written as then gamma, this can be written as gamma at time L of 0 0. Gamma 0 0 is previous state 0, next state is 0, gamma 0 0 into alpha L belonging to state 0. So, this is gamma L 0 0 alpha L 0. So, this is corresponding to this transition. Okay. This is corresponding to this transition, this term will come fine. Now, there is another transition here which is basically this. So, we can write this will be plus gamma L 1 0. So, gamma L 1 0 is the gamma corresponding to this transition when the initial state is 1 and next state is 0, multiplied by alpha at time L belonging to state 1. Okay. So, alpha L plus 1 0 can be then written as this. Now, similarly, we can also compute what is the value of alpha L plus 1 at 1. So, we repeat the same procedure. So, let us write it here, alpha L plus 1 when the final state is 1 can be written as gamma L 0 1 times alpha L 0 plus. So, this is corresponding to this transition gamma L initial state 0, final state 1 and alpha at time L 0 plus this another transition which is this. So, this can be written as gamma L 1 1 times alpha L 1. So, these are for this particular convolutional encoder whose trellis section is given by this, these two are my alpha values, this one and this. So, you can see I can recursively compute alpha at time L plus 1 from alpha at time L and branch matrix gamma. Now, to do this recursion, we need to know what is the initial condition. So, what is the initial condition? So, we need to know what is the value of alpha 0 for different states, for state 0, for state 1. We need to know what the value of these are. Now, note initially we assume that the encoder is in all 0 state. So, if we assume the encoder is in all 0 state, then it is going to stay in all 0 state, then in that case we consider this probability as 1 and this all other possibility of it staying in all the state as 0. So, the initial value when we assume that the encoder is in all 0 state, we assume that alpha 0 at 0 is 1 and at alpha 0 at any other state is non-zero. So, similarly we can compute betas recursively. So, from definition we can write betas in this particular fashion, and again we introduce a new variable s and sum over all possible values of s. So, then this becomes, from here we get this. Now, we split this r into these two terms. So, we get this expression. Now, using base rule I can separate out this term into two terms like this, and we know that, again let us go back to our trellis section. So, 0 0 1 1 1, this is 1 1 0 and this is 0 0 1, this is state 0, this is state 1. So, if you are interested in probability of R t greater than L, that is this is your time L. So, probability of r t greater than L given previous state S hat, next state S and R L, it only depends on. So, if you know the next state S, you do not need information about the previous state, you do not need information about the current bit. So, I can simplify this expression in this particular fashion, and if we go back, this is nothing but our betas and this is our gamma. So, let us compute beta for this particular code. So, we are interested in computing beta L for 0 and beta L at state 1. So, beta L at state 0 would be, so beta L at state 0. So, we are interested in computing beta at state 0. So, this is sum over all those transitions which are ending at this state. So, there are two transitions, one is this one, another is this one. So, let us write the expression for this particular term. This we can write as beta at time L plus 1 times gamma L 0 1. So, the contribution of this is beta L plus 1 corresponding to state 1 multiplied by gamma of this trellis section, gamma L when the initial state is 0 and the next state is 1. So, this will contribute this term plus this another transition which is this one, right. So, we can write contribution of this as beta L plus 1 0 times gamma L 0 0. So, this is our expression of beta L for state 0. Similarly, we can compute beta L for state 1. So, what are the two transitions which are ending at this state? One is this one, other one is this one. So, let us write down the expression for this one. So, this will be beta L plus 1 0 times gamma L 1 0, this is this term, and what about this particular term? This will be given by beta L plus 1 times gamma L 1 1. So, this is our expression for betas. So, as you can see, similar to the expression for alphas, now these betas can be computed using, so alphas can be computed using forward recursion and similarly betas can be computed using backward recursion. So, then we would require the knowledge of beta at time at end of the trellis. Now, how do we know the values of beta? Now, if the encoder is terminated, that means if the encoder is brought back to all 0 state, in that case beta at end of the trellis, at the end of time, let's call beta at time k, which is the end of the block, at state 0 will be 1 and for all other state it will be, for in this case there are only 2 states. So, for all other state this will be 0. This is for the case when the convolutional encoder is brought back to all 0 state, it is terminated. In case the convolutional encoder is not terminated, then we do not know in which state it has ended up with. So, what we will do is, in that case we will assume that it is equally likely to end up at all 0 state or any other state. So, in that case we would assume beta at the end of the block to be equal to 1 by number of states. So, in this case we would assume that beta k 0 is half and beta k 1 is half. So, this is for the case when convolutional encoder is not terminated. That means, it is not brought back to all 0 state, and this will be the initial condition when the convolutional encoder is terminated. Now, next we compute the branch matrix gamma. Now, from definition, gammas can be written like this. So, this can be written as joint probability of being in previous state S prime, next state S, given a received sequence at time L R L divided by probability of being in previous state S prime. Now, this I introduce a term this. So, I add this term in the numerator, and similarly I add this term in the denominator. Okay. Now, this quantity can be written as probability of S given S prime, and this probability can be written as probability of R L given previous state S prime and next state S, which can also be written as probability of R L given transmitted sequence V L multiplied by a priori probability of getting U L. So, note that this probability will be 1 only when there is a valid transition from state S prime to S, otherwise this will be 0. Okay. So, what does gamma depends on? It depends on what is the a priori probability of U L, and it depends on this likelihood function probability of R L given V L. Now, if we consider an additive wide Gaussian noise channel, we can write this probability of R L given V in this particular fashion. So, gamma for an AWGN channel will then be given by this expression. So, note this depends on a priori probability of U L, it depends on the Euclidean distance between R L and V L. Now, let us assume that we are considering a binary phase shift keying. So, in other words, basically we have bits mapped to +1 and -1, let us say, or plus ES and minus ES. Okay. So, let us expand this term and see, can we simplify this term. Now, this term will be common for all the terms, which depends only on signal to noise ratio. And if you look at this particular term, so here there is an R L square term, there is a V L square term, and then there is minus 2 R L V L term. So, this R L square term, that does not depend on what my V L is, and since we are considering a BPSK modulated signal. So, V L, whether U of L is -1 or +1, this will basically be the same, this will be just 1. So, the only term that is changing with choice of V L is this particular term. So, what we can simplify this gamma L, we can just simplify our gamma L like this. So, it is basically probability of U L and exponential minus E S by N naught, and this is basically 2 times R L V L. So, it becomes dot product between the received sequence and this transmitted code, but V L. Okay. So, and of course, there is some constant, there is some constant term K 1 which is common. So, in nutshell then, our gamma depends on this term, right, and it depends on what the initial a priori probability of U L is. So, for an additive wide Gaussian noise channel, when we are employing BPSK modulation, then we can simplify our expression for gamma. So, this can be written as e raised to the power minus E S by N naught 2 times R L dot V L. Now, what is this RL.VL? We will illustrate this with an example when we solve, when we show an example. Okay. So, the point which I am trying to make is that this expression that you see for computation of gamma for an additive wide Gaussian noise, it essentially depends on two terms. One is this and another is this term. Next, I have already specified now that our joint probability of the joint probability that we computed, it is basically a product of three terms alpha, beta and gamma. Now, alpha, beta can be computed in a recursive fashion, and I already mentioned that usually our encoder is in all 0 state to start off with, and that is why we assume that alpha at time 0 is 1 for the state 0 and it is 0 for all other state. Similarly, if we assume that our encoder is terminated, that means it has been brought back to all 0 state, in that case at the end of the block, which is our k, beta k will be 1 for state 0 and 0 for all other states. So, these are our initial condition for computing the recursion for forward recursion as well as backward recursion. So, now then, to recap, how do we compute the a posteriori probability? The first thing is we need to initialize the values of alpha at time 0 and beta at time end of the block, which is I am calling k. The next thing I need to do is, now to compute alpha and beta, I need the value of this branch matrix gamma. So, the first thing I need to do is, I need to compute this branch matrix gamma. So, I will compute this branch matrix for all valid transitions and for all time instances. So, that is the second step. The third step is, once I compute this branch matrix gamma, then I will compute using forward recursion, I will compute the values of alphas, and using backward recursion, I will compute the values of beta. Once I have the values of alpha, beta and gamma, then I can compute the a posteriori probability, because I have shown that it is a basically product of these three terms. So, I can then compute this APP values, and once I have this APP value, I will take a hard decision based on whether this is greater than 0 or plus 1. So, the final thing that I am going to do is, I am going to take a hard decision based on what is the value of this APP value. Okay. So, let us now show this the same using an example. So, we are going to consider an example to illustrate how we can do BCJR decoding. So, we are considering a rate 1/2 convolutional code with memory 1, whose generator sequence is basically given by this. The generator matrix is given by this. We are considering BPSK modulation, and we are assuming that initial probability UL is equally likely to be plus 1 or minus 1. So, we are assuming it is equally likely to be, it is plus 1 with probability half and minus 1 with probability half. We are considering an AWGN channel with SNR of 1/4, and we are assuming that the received signal are normalized by under root EFS. So, what we are receiving is this particular sequence. The question I am interested in is, if the received sequence is this, I am interested in estimating what was my information sequence. So, to solve this problem, what we need to do is, we need to compute the a posteriori L value. Now, to compute the a posteriori L value, we will first have to compute alpha, beta and gammas, okay. And eventually we will compute the a posteriori L value, and then I will take a hard decision on that to estimate our information sequence. So, this is the convolutional encoder that we have considered. This is basically G of D is the rate 1/2 code, and its corresponding trellis diagram is this. For simplicity, I have just considered 4 time instances. So, initially I assumed this encoder is in all 0 state, which is denoted by S0, and it gets some bits. It moves to either S0 and S1 depending on what bits it is received. This is the first time instance, this is first time instance, this is t equal to 2, this is t equal to 3, and then after this what I am doing is I am terminating this encoder back to all 0 state. So, this is the termination phase. So, I bring this encoder back to all 0 state. Now, this is a rate 1 code. So, for each trellis section I am receiving 2 bits. So, at time t equal to 1, what I received is these 2 bits 0.8 and plus 0.1. For t equal to 2, I received these 2 plus 0.1 and minus 0.5. For t equal to 3, I received minus 1.8 and plus 1.1, and for during the termination phase, I received plus 1.6 and minus 1.6. Please note, I am interested in, given this receive sequence, I am interested in estimating what was the information bit that was transmitted at time t equal to 1. What was the information bit that was transmitted at time t equal to 2? What was the information bit that was transmitted at time t equal to 3? So, as we said, the first step is initializing alphas and betas for recursion. So, since we started with all 0 state, alpha at time 0 for state 0 is 1, and for other state which is state 1, it is 0. And since we are terminating this encoder, so beta k times t equal to 4 is 1 for state 0, and it is 0 for other state which is state 1. So, that is the first step, initializing the forward and backward metric for time t equal to 0 and time t end of the block. In our example, t equal to 4. So, once we have initialized our alphas and betas, next we need to compute alphas and betas for other time instances, and for that we would need our branch metric. Now, how do we compute our branch metric? If you recall, for the AWGN channel, we showed that this branch metric can be written as some constant, let us say call it k1 times probability, initial a priori probability UL, and we have exponential plus ES by N naught 2 times RL dot VL. Now, in this particular example, we are assuming that a priori it is equally likely to be plus 1 or minus 1. So, this probability will be half whether UL is plus 1 or minus 1. So, we can just, so this will be a constant. So, we can just include this in a constant thing, and we can just ignore this term. So, what we need to compute the branch metric is basically some k 2 times exponential plus ES by N naught 2 times RL dot VL. Now, in our example, ES by N naught is 1 by 4. If you just go back, ES by N naught is 1 by 4. So, then we can write this as, let us ignore the constant term, I can write this as RL dot VL by 2. Now, how do we compute RL dot VL? Let us take an example. Let us take this gamma at time t equal to 0, when the initial state is S0 and final state is S0. So, what is this? This corresponds to branch metric for this path. This is time t equal to 0, initial state is S0, final state is S0. Now, what is RL? What is the receive sequence corresponding to this trellis section? The receive sequence is given by this. This is plus 0.8 and plus 0.1. Now, what is the VL corresponding to this transition? This is minus 1 and minus 1. So, VL is minus 1 and minus 1. Then this dot product can be written as plus 0.8 into minus 1 plus 0.1 into minus 1. So, this will be minus 0.9. So, RL dot VL is minus 0.9. So, if we plug that in here, minus 0.9 by 2. So, this is minus 0.45, which is given by this. Now, you can take any other example. Let us just take this example, gamma 1 S1 S0. Now, what is this? So, gamma 1 is time instance t equal to 1. So, this we are talking about this, and initial state is S1, final state is S0. So, we are talking about this transition. Now, what is RL corresponding to this transition? It is plus 1 and minus 0.5. So, this is plus 1 and minus 0.5. And what is VL corresponding to this transition? It is given by plus 1 and minus 1. So, VL is plus 1 and minus 1. So, then what would be RL dot VL in this example? It is 1 into 1 plus minus 0.5 into minus 1. So, this will be 1.5. So, you plug that in here, 1.5 by 2. So, this will be e raised to power 0.75, and that is what it is. Okay. So, I hope it is clear how we can compute the branch metric. Please note, we have ignored the common term which is common for computation of all of them. We are just computing the term which will be different based on what state transition that we are considering. So, similarly, we can compute gammas for other time instance t equal to 1, t equal to 2, and for all other valid state transitions. Now, the next step is, once we know our gamma, we have already initialized our alphas and betas. So, the next step would be to compute alphas and betas, and this is shown here. Now, we have already illustrated how we can compute our alphas and betas when we explained how to compute this forward recursion and backward recursion. We can take another example. Let us just take this example, alpha 2 at state S1. So, alpha 2 will correspond to, so this is alpha at 0, alpha at 1. So, this is alpha at 2. So, we are interested to calculate alpha 2 at state S1. So, we are interested to calculate alpha 2 at state S1. So, we are interested to calculate alpha value here. Now, what are the transitions that are ending at this state? One is this, another is this. So, there will be two terms in the alpha computation of this, one corresponding to this transition, which is given by alpha at time 1 S0 into gamma 1 S0 S1 plus there will be another term corresponding to this transition. This will be alpha 1 at state S1 times gamma 1 initial state S1 next state S1. So, this is the value of alpha 2 at state S1, and that is what we have got here. You can check alpha 1 S0, gamma S0 S1, gamma S0 S1, and the next term is alpha S1, gamma S1 S1, alpha S1, gamma S1 S1. So, like this we can compute the values of alphas, and these values that you see are basically the values of alpha computed this way. Now, we can also normalize the values of alphas, because alphas are sum of the alphas over all state should add up to 1. So, in the bracket that you see here, these are the normalized values of alpha. So, how do I get this? So, this is 0.6376 by 0.6376 plus 1.5683. So, this is this quantity. Similarly, this is 1.5683 divided by this one. So, these are the actual values of alpha, and these are a normalized value, because these are sum of probability should add up to 0. So, I can take this value. So, when I compute alphas, or I can just work with these values, or I can work with these values. It is just a scaled version. So, it does not make a difference, except for implementation purpose you may want to scale them, add them up to 1, so that the values do not blow up. So, once we have computed alphas, we can follow the same procedures to compute beta. So, beta computation is given here. Again, we can, as an example, we can take one particular case. Let us just consider this beta 1 at state S1. So, this is beta 0, beta 1 at state S1. So, we are interested in computing beta 1 at state S1. Now, what are the transitions that are ending in state S1? One of them is this, the another one is this. So, what is the contribution from this transition? This can be written as beta 2 S0 times gamma 1 S1 S0 plus, and the contribution from this will be beta 2 S1 times gamma of this. This is gamma 1, this is 1, gamma 1 of S1 S1. So, this, the one in green is corresponding to this transition, the one in red is due to this transition, okay, this transition. So, beta S1 can be written as beta 2 S0, gamma 1 S1 S0 plus beta 2 S1, gamma 1 S1 S1, and that is what we have, beta 2 S0, gamma 1 S1 S0, beta 2 S1, gamma 1 S1 S1. We already know the values of gammas that we have computed earlier, and we know the values of beta at the end of block. What is this value? This is 1, because the encoder is terminated, and for all other state basically beta 4 S1 is 0. So, this is 1, we know these values. So, we can compute what is beta 3. Once we know the value of beta 3, then we can compute values of beta 2, because beta 3's values we will require here. Once we know the values of beta 2, we can compute the value of beta 1, they are required here. So, like that basically we can recursively compute the values of betas. So, now what do we have? We have the values of alphas, we have the values of betas, and we have the branch metric gammas. Next step, we need to compute the APP value. And what is the APP value? If you recall, the APP value, it was product of 3 terms, alpha, gamma and betas. So, product of this term. And what was the term in the numerator? We were summing over all those transitions which belongs to u being plus 1, and in the denominator we were summing over all those transitions belonging to u being minus 1. So, let us look at how we can compute this. So, let us look at first case at time. So, u0 is the information sequence that we are trying to estimate for time, first time instance t equal to 0. So, this is, we are looking at this trellis section. Now, which are the transitions corresponding to ul being plus 1? So, I am denoting by blue the transitions which is corresponding to ul being plus 1, and I am denoting by green the transition corresponding to ul being minus 1. Okay. Then in the numerator, then I will have one term corresponding to this transition, and what would be that term? It will be alpha 0 s 0, then gamma corresponding to this transition, which is gamma 0 s 0 s 1 times beta 1 s 1. So, I have alpha 0 s 0, alpha at this state, gamma corresponding to this transition, which is gamma 0 s 0 s 1, and beta corresponding to this state. So, if you go back, this is what I have: alpha 0 s 0, gamma 0 s 0 s 1, and beta 1 s 1. At this time instance, is there any other transition corresponding to ul plus 1? No, there is only one transition corresponding to ul plus 1. So, we will now look at the denominator term. So, we have to look for all those transitions corresponding to u being minus 1, and there is only one such transitions. So, the denominator term would be alpha 0 s 0, gamma 0 s 0 s 0, and beta 1 s 0. So, this is what we have: alpha 0 s 0, gamma 0 s 0 s 0, and beta 1 s 0. So, we can then calculate the what is the a posteriori L value. Now, let us take another example. Let us take for the second time instance. So, the second time instance, we are interested in estimating what was our information sequence or information bit. So, we are now looking at this time instance, Okay. Now, what are the transitions corresponding to ul information sequence being plus 1? One of them is this. You can see the information sequence is plus 1, that is when you go from s 0 to s 1, and another transition is this one. So, these are the two transitions corresponding to ul being plus 1. So, in the numerator you will have two terms, one corresponding to alpha 1 s 0, gamma 1 s 0 s 1 times beta 2 s 1, and another term corresponding to this transition, which is alpha 1 s 1 times gamma 1 s 1 s 0 multiplied by beta 2 s 0, and that is what you see here. There are two terms, one is alpha 1 s 0, gamma 1 s 0 s 1, beta 2 s 1. This corresponds to this transition, and the next term that you see here, this one, corresponds to this transition. Okay. Now, similarly, in the denominator, you need to look at what are the valid transitions corresponding to ul minus 1, and what are those? One of them is this, and the second one is this. So, now in the denominator also you will have two terms, one corresponding to this transition, other corresponding to this transition. This transition will give you alpha 1 s 0, gamma 1 S0 S0 times beta 2 S0 plus alpha 1 S1 gamma 1 S1 S1 times beta 2 S1, and that is what you have here. So, likewise we compute log likelihood ratios, APP values for all the 3 information bits. Now, what is the final step? Once we have computed the log likelihood ratio, we will see whether these log likelihood ratios are greater than 0 or less than 0. If they are greater than or equal to 0, we decide in favor of UL being plus 1, otherwise we decide in favor of UL being minus 1. So, this is 0.4778, which is greater than 0. So, we decide in favor of plus 1. This is greater than 0. So, we decide in favor of plus 1, and this one is less than 0. So, we decide in favor of minus 1. So, then the final decoded bits are plus 1, and minus 1. So, with this I will conclude this lecture. Thank you.